Welcome. In this video, we will be taking a look at the introduction to limits. This is our second lecture in our brief calculus course in section 2.2. So let's take a look at a few definitions to get started. We wanted to build a strong foundation when we look at the idea of limits, and then we'll take a look at some graphical examples later in the video. So first, a definition on functional values, just a very bare definition, is a functional value describes a function's output at a single point. So if I'm considering a functional value, I'm really just thinking where is the actual function defined, and that would be on the y-axis where a function is defined. A limit value is a whole another concept. So a limit describes a function's how a function behaves as it approaches a point. And that's an important distinction that we want to make today, is this idea of a functional value where my function is defined, and the limit value at a point on the function is very different. One is describing where it actually exists and is defined, and the limit describes where it actually is approaching, even though we might not have a defined point on that part of the function. So just as a view of kind of another concept like a two-sided limit, that's the first type of limit that we'll talk about, and we'll try to view this picture here on the right to describe these terms. We would say that a two-sided limit, as x approaches a value c, in this case we have an a, so if you wanted to represent that with a c, that would help a little bit better. Or really, we could use an a and just change this, because this rest of the notation is an a. We'll just say that's an a. As a approaches f of x is L, and L is a value on the y-axis if the values of f of x get very close to L as x gets very close to a from both sides. So it's a lot of words with this definition, but let's try to break it down with this graph. I want to know, as my inputs get closer and closer to this point of a, what is the height of my function approaching? Or what is the f of x or y value of my function approaching? And in this case, regardless if there is, say, an open circle here or a filled in circle, regardless if that's defined or an open circle or a gap in the graph, we would say that the function approaches L as our inputs approach the value a on the x-axis. And that's the concept of a limit. Again, it doesn't matter if we actually are defined at that point, or if there's some sort of hole in the graph or a vertical asymptote. As long as we're approaching that same value, we would have a limit. And again, the solution to the limit is the height on the graph that I'm approaching. So let's consider some notation with this limit. So when I consider the limit of f of x as x approaches a is L, this would be notated as, again, the limit as x approaches a. That would be our limit form. This is the function we're taking the limit of, and L would be the actual limit value. So again, this L value is some y coordinate or y value for an input value a, and that's later going to become an actual constant number. And this is the function we're taking a limit of. So this would be the two-sided limit notation, a two-sided limit where we approach from both the left and the right side. Couple notes on this limit concept. Again, this limit concept is not the same thing as saying the functional value f of a is equal to L. That could be true, but it is not asking the same question or answering the same question. Sometimes the limit at x equals a will be the same value as the functional value, but they are not asking again the same question. And then the limit as x equals a may exist even though the functional value is undefined. So we can't have a limit when our function is undefined. A couple other limit notations we'll take a look at are the one-sided limits. So we just talked about the two-sided limit where we approach from left and right. Here we can think about what if we just consider the left or the right side individually. So we can say that the left-sided limit as x approaches a of f of x is m if the values of f of x get very close to m as x gets very close to a from the left of a. So the notation for a left-sided limit changes just slightly. Notice that we have x approaches a minus, and that means that we're approaching from the negative end of our graph. So just to start maybe drawing a little picture to describe what's happening here, we can consider just a function. Doesn't matter what the specific look is. But let's consider that this is our point A on our x-axis. We would say that to describe this limit here, we would say that the limit as we approach from the left side is going to equal this m value. This would be the picture that would describe the same left-sided limit. So we are approaching only from the left side here. And as we approach a from the left side, we are reaching this point of m. Again, it doesn't matter that this is an open circle or a closed circle. It just matters if we're approaching that value as our input approaches a. The other one-sided limit that we'll be interested in is the right-sided limit. So if I consider a right-sided limit as x approaches a of f of x, this is going to be n if the values of f of x get very close to n as x gets very close to a from the right of a. And again, we'll notice a notational difference here in the limit where we have x approaches a plus. A plus just means we're coming from the positive end of my graph. That means from the right. So if I'm coming from my positive end of my graph and I'm approaching a height of n, we could augment our previous picture here and say as we approach from the right side of our graph, coming this direction, we would say that this limit is approaching the height of n, which happens to be a little lower than the value of m. Again, m and n here are going to be real numbers on the y-axis. So both of these values represent y values. And they may or may not be defined. So here, A's actual functional value, and this is kind of a third question, is we could ask, well, in this little diagram, we could say, well, what is the functional value at A? Well, it can't be both n and m at the same time. In this case, it happens to be n because that's where the point is actually defined. So again, this is asking a totally different question than the limit as we go from the left or the limit as we come from the right. This third question is where are we actually defined? And here we would say we're defined f of a at the value n. Again, that's a y value again. Okay, so those are our those two one-sided limits. It's kind of a tongue twister. Let's take a look at a couple notes for these. One is the limit as x approaches a of f of x is equal to L. That's the two-sided limit. If and only if the one-sided limits are equal to that same value. So we want the limit as x approaches a from the left and the right to be equal to that same quantity L. If that is true, that means we're approaching the same height from both the left and the right, and by definition, we would have the two-sided limit at L. If those two-sided limits do not agree, or the one-sided limits do not agree, that two-sided limit we would say does not exist. And we'll see that in our graphical examples in a minute. So feel free, if you'd like, to go back in any steps in this discussion with these definitions. We're going to take a look at some graphs next. And before we take a graph, let's take a look at maybe just how do we talk about limits, how do we describe them in words, and then we'll jump down to these graphs. So part A, part B, and part C here are three ways we can describe limits. One is a two-sided limit, one is a left-sided limit, and then part C is a right-sided limit. So the first one we can describe in part A is the limit of 2x plus 7, that's our function, as x approaches 4, we would say that is -1. If we describe part B, we'd say that the limit of t squared plus 5t as t approaches 2 from the left is 14. And then the last one, we would say the limit of our function h cubed minus 27 as h approaches 4 from the right is 37. So the limit is equal to 37 as we approach from the right. So just if you try to think about how we actually say those limit notations in a statement there, that's a concise way to say each of those limits, the one-sided limits, and then the two-sided limit in part A. Let's take a look at a few graphs here. We'll start with this graph of f of x. We'd like to go through and find each of the limit and functional values. So let's consider the first part A. We want the limit as x approaches 2 of f of x. And so we know that's a two-sided limit. So we're approaching from both ends. If I look at my graph and approach the value of 2, this happens to be a value that's defined on my graph. If I look at my graph, this is approximately a height of 1, we'll call it. And as I approach both sides, I am approaching that same functional value. So in this case, the functional value and the limit value are the same. So we say that is approaching 1 from both sides, a height of 1. The next limit says we want to find the limit as x approaches 3 minus. Again, that's coming from the left side. If you want to note each of those as we go from the left, we will have that little minus sign. And so as we approach the input 3 from the left, we'll notice that from the left here, it looks like we're approaching this open circle. And that happens to be here the height of 2. So in red, we see that as we approach 3 from the left side of our graph, we're approaching the value of 2. It's an open circle, but we don't care if it's actually defined. We just want to know where we are approaching, and that would be the value 2. If we approach from the positive end, the limit as x approaches 3 plus, that would be approaching from the right. And we could say as we approach from the right side, we're actually approaching a new height, and that height happens to be up at 3. So as we approach x equals 3 from the right, we are approaching the height of 3. So here's an example where we can take a look at the two-sided limit at x equals 3 and consider, well, we're approaching 3 from the right and we're approaching the height of 2 from the left. And so here is where those two one-sided limits do not agree in part B and C. And so we would say that in part D, this two-sided limit does not exist. We say that does not exist. If we consider part E, we have the functional value at 2. So if I consider that functional value at 2, we just said earlier that the value 2 is defined. It's on a continuous part of our function, and so that functional value happens to be at the height of 1. So we can fill that in. And then last but not least, we have the functional value at 3. Notice that we have two open circles, both when we approach from the left and the right. And so here we could say that that function is undefined at 3. Or we could say that functional value really does not exist. If you're doing this through our more homework system, you'll want to use this phrasing of does not exist for that f of 3 in that case. So our function is undefined at 3, so therefore this functional value does not exist. We'll take a look at a couple more graphs as we move along here. The next graph has a few gaps in it, a few holes in the graph. So let's go one by one. We have part A takes a look at the limit as x approaches -3 from the left again. So if we approach -3 from the left side of our graph, we'll notice that I am coming up on this functional value here, and that looks like at a height of 4, so I would say that that limit value as we approach from the left is 4. As I approach from the right side, in part B, the plus sign there tells me I'm approaching from the right. We are approaching this value down here, which happens to be at a height of -2, that hole in our graph. So again, we could say that this function is has two results for our one-sided limits. One's going to 4, one's going to -2, and so that two-sided limit here in part C, we can say does not exist. Those two one-sided limits do not agree. So again, that would say that the limit as x approaches -3 does not exist. It's going in two different directions. We can look at the next limit in part D. If we look at as the value of x approaches 2, well, that's a two-sided limit, so we want them both to approach the same height, and it looks like they do. Those will approach the height of 1 as x approaches +2. If I consider the value as the limit as approaches -1, that's also a two-sided limit. And we could say that this one also approaches here, this open circle, from both left and right at the height of 1. But notice that the functional value actually is not in that same spot. So this is a case where our limit value exists, but our functional value, f of -1, is actually somewhere else. It happens to be up here at this defined point up at 3. So this is kind of like a jump point where that singular point jumps to another part of our graph and breaks that chain or that curve up into segments. So we'd say the functional value is where we're defined, that's at 3. And so our limit value, again, is talking about a totally different thing of where we're defined. Where we are approaching is -1, or at +1, and where we are actually defined as a point is at +3. The last few are going to be functional values as well. If we look at f of -4, we're looking at the functional value at -4. And for this one, we'll just call that approximately 2.5 as a height. If we look at the value for f of 2, the functional value at f of 2, if we look here, we have an open circle at +2, and there's no other defined point here, so we could say where function is undefined at 2, and so this does not exist. There's no functional value that would not exist there. And then finally, last but not least, we have f of 3. F of 3, we can go and follow our function. This happens to be part of the line there, and we could maybe call that 4 1/3 or 4 1/4. So we can maybe just call that maybe 4 1/3. I'll put it as decimal maybe. Something like that. 4 1/3. If we wanted to be more exact with that, we could say maybe it's 13/4. That would be, that would be 17/4. If we wanted to write it in kind of a fraction form, that would be the same as 4 1/4. So let's call it 4 1/4 then. Something like that. The next graph that we'll take a look at, we have a couple more to do. One looking at limits at infinity. These look a little bit different than the ones that we've done so far. So let's maybe take a look at the notation first, and then we'll try to find them based on the graphs. So our first one in part A looks at the limit as x goes to -infinity. So this is a little bit different than either the two-sided limit or the one-sided limit concept where we're actually approaching a real number value. Here we're approaching a value of infinity or -infinity in part A. So let's take a look at our graph and see what we're actually trying to look for here. If I want to consider my inputs decreasing without bound, I'm going to be considering really what's my function doing as I go off the page, or what would be, in other words, my end behavior on the left side, my left-hand end behavior. So based on what we see here, there looks like to be somewhat of a trend here, and we'll have to kind of consider extrapolating this a little bit, but it looks like we're kind of leveling off here. Looks like at a height of 1. And so we're going to be, again, considering where is my function going in terms of the height, what y value are we starting to approach as x goes to -infinity. And for us, I would say we're going to be approaching here at this value of +1. So there might be kind of a horizontal asymptote kind of forming right there at +1. Taking a look at the other side of the graph, if we look at x going to +infinity, that's really our right-hand end behavior. We can see as we approach +infinity, our graph is increasing without bound, and so that would be going to +infinity. So as x goes to infinity, our y values are also increasing to infinity. So we'd say that one is going off to +infinity. C and D, we have a collection of one-sided limits one more time. And so this says, what is the limit as x approaches -2 from the positive end, or the right side of our graph? And so we can look at -2 from the right side of our graph. So from the right, looks like our function there is approaching straight down, which would be tending off towards -infinity. It's not going to stop there. So as I approach -2 from the positive end of my graph, I could say I'm going down to -infinity. If I approach that same -2 input from the left side, with the -2, 2 on the negative side of my graph, that's this part of the graph. Notice that we have kind of an asymptote here at -2 where we're not defined. But on the left side, looks like we have a curve that's approaching positive infinity. So we'll say positive infinity for that. A couple more limit values would be at as x goes to -1. So as x goes to -1, we could say from both sides, the left and the right, it appears like we are again approaching a common value. It happens to be that hole in the graph right in the middle at -1, 1. And so we're approaching that value of 1, even though we're not defined there. We could say we're approaching the height of 1. The limit as x goes to 3, we look at the limit as x goes to 3, looks like we have a filled in functional value here. Happens to be the same as the limit since we're on a continuous portion of our function. And that height looks like it's at a value of 4. We follow that over. So as x approaches 3, our function is approaching 4. And then last but not least, we have a couple functional values, one at -1. If we look at the functional value at -1, that's this jump point that pops over to +3. There's where we're actually defined at -1. And then f of 1, we could say the functional value at 1. Looks like we have a hole in our graph at 1. So we're undefined at 1, and so this functional value does not exist. There's no functional value. You could say that's D and E, does not exist. We have one final graph to take a look at just for some extra practice and look at the graph. We'll start with a collection of limits at the value 3. We can consider the limit again as x goes to 3 minus. That's another left-sided limit. So we go from the left on this graph. We are approaching that filled in circle at the height of 3. If we go from the right with 3 plus, the limit as x approaches 3 from the right of our g of x function here, we would say that we're approaching this hole in our graph where we jump down, and that's at the height of 6. And again, this is a case where those one-sided limits do not agree. We're not going in the right space there. One is approaching 6, and the left side is approaching 3, and so that two-sided limit that we have at x as x goes to 3 it does not exist. So D and E could be another appropriate label there. That one-sided limit does not exist because the two one-sided limits do not agree. The final limit that we'll evaluate here is as x goes to infinity. This looks kind of similar to the previous graph. As x goes to infinity, the right-hand end behavior, it appears like our graph is going off and tending towards infinity again. And we'll finish off with 4 different functional values here. We have the functional value at 5. We'll notice that at 5 we have another hole in our graph. That's undefined. And so we would say this functional value does not exist. G of 7 does have a functional value. It doesn't happen to be where the limit value would be. If we set the limit as x approaches 7, that would be at the value 4, where that open circle is, but our functional value is down here at 7, 2. So at the height of 2, we'll have a functional value. G of 3, we can see that we are defined at G of 3 right here at the point 3, 3. So that functional value is the height at 3. And then last but not least, we have the G of 6. And so G of 6 is kind of at this bending point of our V. And we can assume that we're actually defined there. I think that graph shows that we are actually defined there. It doesn't necessarily have a point, but the graph passes through. And we'll say that G of 6 here is at that hinge point at the height of 3 as well. So this wraps up our discussion with limits and as an introduction, taking a look at graphical examples. In our next video, we will take a look at the ideas of continuity and consider algebraic limits as well. So thanks for watching. I'll see you in the next video.